Hello, my dear, and let's start our lecture number 2 on hypersonic dynamics. This lecture topic is inviscid hypersonic flow. And this module is short and sweet. Shock waves and expansion waves are ubiquitous features in supersonic and hypersonic flow fields. The detailed analysis and calculation of shock and expansion wave properties are bread and butter topics in the study of compressible flow. Are you agree with me? Okay. And in this case, I want to say next. This module goes a step further. Here, the assumption of a very high Mach number ahead of the waves allows the rather elaborate, but exact shock and expansion wave relations to be reduced to much simpler, albeit approximate, equations that hold for hypersonic flow. And you might ask, so what? Indeed, for an accurate calculation of the details of hypersonic flow, you should always use the exact shock and expansion wave equation. The value of this module lies elsewhere. It lies in the world of hypersonic aerodynamic theory, first of all. And this module is the front end of the beautiful intellectual triumph that are the foundation of the hypersonic aerodynamic theory to be developed in subsequent modules. One such theory is hypersonic similarity, to be explained in and developed in module 4. But right away, in the present module, the approximate hypersonic shock and expansion wave relations expose one of the most important parameters in hypersonic aerodynamic theory, the hypersonic similarity parameter. Okay? But we are getting ahead of ourselves. For right now, just sit back and enjoy the clean and neat development of the simplified equations for shock and expansion waves afforded by the assumption of high Mach numbers in the flow ahead of the wave. Okay? So let's continue our presentation. Then store this hypersonic shock and expansion wave relation on your mental bookshelf for future use in subsequent modules. Okay, let's go. So today's exactly lecture called hypersonic shock. Consider an airplane flight at Mach 28 as the outer regions of the Earth's atmosphere, say at altitude of 120 kilometers. Upon descent into the lower region of the atmosphere, the aircraft can follow one of the lifting trajectories shown on the altitude velocity map of this slide. The purpose of this figure is to emphasize the obvious fact that such hypersonic vehicles encounter exceptionally high Mach numbers. Moreover, the flight path remains hypersonic over most of its extent. And this figure justifies the study of high Mach number flows and underscores the question: what happens in a purely fluid dynamic sense when the Mach number becomes very large? How do you think? And this question has particular relevance in regard to the basic shock and expansion wave relation. In the present module, we will obtain and examine the limiting form of both the conventional shock wave equation and the Prandtl-Meyer expansion wave relation when the upstream Mach number increases toward infinity. Okay? And these limiting forms are interesting in their own right. However, of more importance, they are necessary for the development of various envisaged hypersonic theories to be discussed in subsequent modules. So let's start with the basic hypersonic shock relation. Anytime a supersonic flow is turned into itself, such as flowing over a wedge, cone, or compression corner, a shock wave is created. Okay? Also, if a sufficiently high back pressure is created downstream of a supersonic flow, a standing shock wave can be established. Such shock waves are extremely thin regions, on the order of 1,025 centimeters in air, across which light changes in density, pressure, velocity, etc. occur. And these changes take place in a continuous fashion within the shock wave itself, where viscosity and thermal conduction are important mechanisms. However, because the wave is usually so thin, to the microscopic observer, the changes appear to take place discontinuously. And therefore, in conventional supersonic aerodynamics, shock waves are usually treated as mathematical and physical discontinuities. As the Mach number is increased to hypersonic speeds, no dramatic qualitative difference occurs. The same exact shock relations that are obtained in supersonic aerodynamics also hold at hypersonic speed. However, some interesting approximate and simplified form of the shock relations are obtained in the limit of high Mach number. These forms are obtained next. Consider the flows through a straight oblique shock wave, as sketched in this figure. Upstream and downstream conditions are denoted by subscript 1 and 2, respectively. Okay? For a calorically perfect gas, I mean constant specific heat, and hence we can write that the gamma proportional Cp over Cv, it must be constant. Okay? And the classical results for change across the shock are given in any standard textbook on compressible flow. To begin with, the exact oblique shock relation for pressure ratio across the wave is given by following. You may see on this slide. Exactly, we may write as P2 over P1 proportionals 1 plus 2 gamma over gamma plus 1 in time on this expression in the bracket, m1 squared sine squared beta minus 1. Beta here is the wave angle. And the limit is the limit of m1 goes to infinity. And in this case, the term m1 sine squared beta must be many times higher than 1. And hence, our first equation from here becomes the following expression, as we can see in this bracket. P2 over P1 proportional to gamma over gamma plus 1 times m1 squared times sine squared from beta. In a similar way, the density and temperature ratios are as follows, as you can see here, if m1 becomes to infinity. Rho 2 over rho 1 will be proportional as gamma plus 1 over gamma minus 1. Analogically, as Mach, the same situation with temperature too. T2 over T1, proportional relations between P2 over P1 and over rho 2 over 1. This leads from the equation state, as you can see in this side of the slide, P proportional to rho R T. Okay? Analogically, in case when M1 becomes to infinity, the relation between temperature T1 and T2 must be expressed by this expression here. This writes as the gamma and proportional to the m1 squared sine squared beta. Okay? So, returning to our previous figure, we must note that our U2 and V2 are the components of the flow velocity behind the shock wave, parallel and perpendicular to the upstream flow, not parallel and perpendicular to the shock wave itself. Okay? As in the frequently done. With this in mind, the following is, so we may write exactly next expression. U2 over V1 will be proportional 1 minus, in nomination we have 2 in bracket m1 squared sine squared beta minus 1. In denomination, we have two components, gamma plus 1 times m1. In case when m1 becomes to the infinite value, we can get this simple expression. U2 over V1 will be proportional 1 minus 2 sine squared beta over gamma plus 1. And next expression will be kept as a relation between V2 over V1. As you can see here, it must be 2m1 square in bracket sine square beta minus 1 times cosine beta. And denomination, we can get the next two components, as you can see in first expression, identical, right? Gamma plus 1 times m1 squared. For larger m1, this expression can be approximated by this one. We may write and that V2 over V1 get us the last expression here. 2 sine beta times cosine beta over gamma plus 1. Because 2 sine beta times cosine beta get us sine 2 beta, then we can write from the previous equation here, in case m1 gets to infinity, we may get this very nice expression, V2 over V1, V capital 1, proportional sine double beta over gamma plus 1. In the preceding, the choice of velocity components parallel and perpendicular to the upstream flow direction, rather than to the shock wave is intentional. I agree with you. Okay, let's go on. So our equation, the last three equations, will be used to great advantage in subsequent modules to demonstrate some physical aspect of the velocity field over slender hypersonic body. So note from this left equation that both P2 over P2 over P1 and essentially T2 over T1 become infinitely large as M became to the infinity. In contrast, rho 2 over rho 1 and U2 over V1 capital and V2 over V1 capital approach limited finite values as M became to infinity. In aerodynamics, pressure distributions are usually quoted in terms of the non-dimensional pressure coefficient, Cp, rather than the pressure itself. So the pressure coefficient is defined as this first expression on the top right side of the slide, Cp proportional, P1 minus P2 minus P1, over Q1. Here P1 and Q1 are the upstream of free stream static pressure and dynamic pressure respectively. In later module, we will use the subscript infinity to denote free stream conditions, such as the free stream pressure, right? And free stream dynamic pressure Q. However, consistent with standard shock wave nomenclature, we denote the free stream condition by the subscript 1 in the present section. Okay? By definition, the dynamic pressure is given by the second formula on the right. 1 proportional 1 over 2 rho 1 times V1 capital squared. And this is definition only. It is used for raw flow from incompressible to hypersonic. And we should note it. For incompressible flow, Q1 and this expression is exactly the difference between the total and static pressure of the free stream. For all other aerodynamic speed regimes, this expression is a definition only, which no exact physical significance. So in high-speed flux theory, it is convenient to express our Q1 in terms of Mach number and pressure M1 and P1, rather than velocity and density V1 capital and rho 1. Okay? And this is easily accomplished by recalling that the speed of sound, our A1, equals square root from gamma P1 over rho 1, and that the Mach number M1 proportional V1 capital over A1. And hence we can get this expression over to 1. Q1 proportional this one essentially get us final expression gamma P1 half over 2 times V1 capital squared over A1. Or simply Q1 we may write as half gamma times P1 and times M1, where this last equation is a very convenient expression for dynamic pressure and can be viewed almost as an alternative definition of Q1. And we can now write the pressure coefficients as these next expression for Cp. It equals P1, P2 minus P1 over Q1. And we can rewrite this as 2 over gamma M1 squared times component in parentheses P2 over P1 minus 1. Combining last two equations, we obtain the exact relation for Cp behind the oblique shock wave as follows. And that we can see on these final expressions here. Cp will be proportional 4 over gamma plus 1, and second component in parentheses sine squared beta minus 1 over m1 squared. Okay? In the hypersonic limit, the following is shown as a net, as we can write as m1 became to infinity. So we may write Cp as these first nice expressions. Cp will be proportional for two components first, 4 over gamma plus 1 in parentheses here, right? Times sine squared from beta. So the relationship between Mach number m1, shock angle beta, and deflection angle theta is expressed by the so-called theta beta m relation. And exactly we may write this expression for tangent of theta. Deflection angle theta, proportional to cotangent beta, and this expression on the brackets here. Right? This relation is plotted on our right figure, which is standard plot of wave angle versus deflection angle with Mach number as a parameter. From this figure, note that in the hypersonic limit, when theta is small, okay, and beta is also small, and hence, in this limit, we can insert the usual small angle approximation in as writing in this expression. So we may approximate as a sine beta simply as roughly a beta, cosine 2 beta nearly 1, tangents from theta get us the same as nearly same sine theta, and simply as a theta. And they get us a result for theta exactly this, I just want to exactly theta 2 over beta, next component in parentheses, m1 squared beta squared minus 1, and over the m1 squared times gamma plus 1 plus 2. Okay? So this expression we can find shock wave angle beta over deflection angle theta. Applying the high Mach number limit to the last derivation, we can get this expression we just saw. In our equation, m1 cancels, and we finally obtain in both the small angle and hypersonic limit, as we can see, as m1 becomes infinite, and theta hence beta is small, then we can write this simple, a very nice expression. Beta over theta get us gamma plus 1 over 2. Very nice. Yes. Note that gamma get us 1.4. We may write more simple expression, beta proportional 1.2 theta. Okay. It is interesting to observe that in the hypersonic limit for a slender wedge, the wave angle is only 20% larger than the wedge angle. a graphic demonstration of a thin shock layer in hypersonic flow. Check this figure on the right, drawn from exact oblique shock result, and note that the 18-degree shock angle is 20% larger than the 15-degree wedge angle at Mach 36. Truly an example of the hypersonic limit. For your convenience, the limit in hypersonic shock relation obtained in this module are summarized in this figure. And this limiting relation, which are clearly simpler than the corresponding exact oblique shock relation, will be important for the development of some of our hypersonic aerodynamic techniques in subsequent modules. So, let's start another topic of today's lecture called hypersonic shock relation in terms of the hypersonic similarity parameter. In the study of hypersonic flow of a slender body, the product M1 and theta is an important governing parameter, whereas before, M1 is the free stream Mach number, right? And theta is the flow deflection angle. Hope you remember. Okay? Indeed, we will demonstrate in later parts module that M1 times theta is a similarity parameter for such flow. And denoting M1 times theta by K, we state this expression, hypersonic similarity parameter. In our future discussion, it will be helpful to express the oblique shock relations in terms of K capital. As you can see, hypersonic similarity parameter. Particularly in the case of pressure ratio, hope you remember, P2 over P1. This is the purpose of the present section. Return to the exact theta beta M relations given in before as expressed. This is an explicit relation for theta proportional from beta. Obtaining the exact inverse relation, beta will be proportional from theta, is tedious. However, in the combined limit of hypersonic flow and small angle, an approximate explicit relation for beta from theta can be obtained. And this will be our first step toward introducing as a K proportional for M1 times theta into the shock relation. And specifically for small angle reduces for this expression, we may write next expression M1 squared times beta squared minus 1 will be proportional to components left side this M1 squared plus times gamma plus 1 over 2 plus 1, and second component beta times theta. In this equation, we may assume that M1 is large and finite. So we may conclude that half 1 over 2 gamma plus 1 times M1 squared must be many times higher than 1. Okay? However, because beta is small, we cannot assume that M1 squared and beta squared is large compared to unity. With this expression on the left, we may write this expression here. m1 squared times beta squared minus 1 will be proportional gamma plus 1 half times m1 squared beta theta. And all of that, after rearranging, we can get to equal the zero. This is a quadratic equation in terms of beta over theta. And solving by means of quadratic formula, we can get this last expression. Beta over theta proportions gamma plus 1 over 4, first component, and the next component under the radical, gamma plus 1 over 4 squared plus 1 over m1 squared times theta squared. In this equation, the minus sign of the radical has been ruled out. It would produce the non-physical result of a negative beta to theta. And good for the limit of hypersonic Mach numbers and small angles. So now return to our previous equation, which is an exact relation for the pressure ratio across an oblique shock wave. And assuming small angle, this becomes our expression for P1 over P2. That get us this expression, 1 plus the same two components, 2 gamma over gamma plus 1, and second component on the parentheses, m1 squared beta squared minus 1. If we wish to apply to this equation at hypersonic but finite Mach numbers, we repeat again that also m1 is large. The product m1 beta might not be large. And hence, for this case, our equation here for P2 over P1 cannot be reduced further. However, within the framework of this assumption, our base equation gives an explicit relation for beta from theta, which can be introduced in our equation here to obtain an expression for P2 over P1 in terms of deflection angle theta. This is carried out as follows. So combines previous equation, we can get for P2 over P1 expression, this expression. Beta over theta squared get us 3 components. Gamma plus 1 over 2 in parentheses here, and plus third component 1 over m1 squared theta squared. For transforming it from the beta square, we get us this expression here. Okay? After substituting in this expression into the previous one, we obtain this final expression on the bottom of this slide for P2 over P1. Okay? Nice. You may repeat your personally too. And now, again, denoting m1 theta by k, our equation will be written as this expression for P2 over P1. Exactly get us 1 plus second component gamma times gamma plus 1 over 4 times k squared. Plus second component here, j k squared times radical from gamma plus 1 over 4 squared plus 1 over k squared. This equation is the desired result. It gives the pressure ratio across an oblique shock wave in terms of the hypersonic similarity parameter, subject to the combined assumption of high but finite Mach number and small angle. Okay? Because the pressure field behind a two-dimensional oblique shock is constant. It also gives the pressure P2 on the surface of the wedge of deflection angle theta. Round out our present discussion associated with the hypersonic similarity parameter, consider the pressure coefficient defined earlier, and after substituting in our final equation, we get obtained expression for Cp here. For multiplying and dividing by theta square, we get expression for Cp at the bottom of this. Or we may write is more compact expression at this line. Cp proportional first component to theta square, in second components in parentheses, gamma plus 1 plus over 4 plus radicals from gamma plus 1 over 4 square plus 1 over k square, identical as this. Okay? But we should note it from this equation here that for hypersonic flow over wedges with a small deflection angle, Cp over theta square will be a function from k and k. We will find later that relations analogous to this expression abound in the theory of hypersonic flow over slender body. Now, let's come to the next part of our lecture. This topic calls hypersonic expansion wave relation. Consider the center Prandtl-Meyer expression around a corner of deflection angle theta is sketched in this figure on this right. Okay? So an expansion fund consisted of an infinite number of Mach waves originate at the corner and spread downstream, as you can see. The Mach number and pressure upstream of the wave, you can see here, M1 and P1 respectively, right? The corresponding quantities downstream of the wave, yes, you see M2 and P2 respectively. From the basic compressible flow, the relation between theta M1 and M2 is given by this first expression on the left side of the slide. Theta proportional to V from M2 minus V from M1, right? Where V is a Prandtl-Meyer function here of the net. Radicals, first component, radical gamma plus 1, gamma minus 1, and second components here, tangents over tangents, and radicals next, gamma minus 1 over the gamma plus 1 times M1 minus 1. And third part of this is inverse tangent times the square root from M squared minus 1. For large Mach numbers, this expression will be approximately as a M sub. And hence, our last expression here can be written for supersonic flow as this one, V from M, theta, first expression without change, right? Tangents in 1 minus 1, and this expression identical, but now later we can get more simple. M simply minus inverse tangents over M. Recalling the trigonometric identity, we know that inverse tangents for X get us half pi minus inverse tangents from 1 over x. And we obtain the combining equations to previous for inverse tangents 1 over x, this expression, right? And inverse tangents for x, phi minus 1 over x, 1 plus minus plus minus. Yeah? Okay. Here m is the frontal Maya function. So we might write this expression, frontal Maya function, v from m. Yes? That's one component, second component, third component here. Okay? For large Mach number, we might say as radical from m squared minus 1, you remember as the previous slide, approximately equal m. And hence, our last equation can be written for the hypersonic flow as this one. V from m, for first component square root from gamma plus 1 over gamma minus 1, inverse tangent from radical opposite, yes? Gamma minus 1 over gamma plus 1, and after that times m minus inverse tangent over m. Recalling the trigonometric identity, inverse tangent from x get us half pi minus inverse tangent over inverse x. Yeah, and the series expansion get us the same, 1 over x minus 1, 3x cubed plus 1 over 5x5, x in power 5 minus 1 over 7 x in power 7 plus minus sign. Inverse tangent for the x, yeah, obtaining, combining previous two, we can get as this one, half pi minus 1 over x plus 3 times x cubed minus plus minus 1 over 5 x in power 5 and plus 1 over 7 times x7. Okay? In this case, we can utilize all these expressions, and we can rewrite expression for v from m as this one. At high Mach number, the higher order terms associated with this big expression, that is terms such as 1 over 3 m cubed, 1 over 5 m in power 5, etc., can be ignored. Yeah, because it became so small. For this case, our equation, this large equation, may be used as more simple form, like here. V from m get us first components radical 1 gamma plus 1 over gamma minus 1 times half pi. Yes, and minus second component in parentheses gamma plus 1 over gamma minus 1 times 1 over m, and minus half pi e plus 1 over m. Or we may rewrite this expression in this more convenient sign, or rewrite as this one. Theta proportional to gamma minus 1 minus, in parentheses, this picture is closed for you. It will be 1 over m1 minus 1 over m2. Okay? So this equation is the hypersonic relation for frontal Maya expansion wave. It is an approximate relation that becomes more accurate as m1 and m2 become larger. Recall that m increases through an expansion wave, and hence theta in our equation here is a positive quantity. And this is consistent with the sketch down on the previous figure. Yeah, I just did that. Yeah, we remember. Okay? Where the deflection angle theta is treated as a positive quantity. So the flow through the expansion wave is isentropic. And hence, the isentropic pressure relation holds as follows. As you can see here, P2 over P1 expression in bracket and power gamma over gamma minus 1. For large Mach number, the hypersonic approximation for this one becomes more simple expression like P2 over P1 proportional M1 over M2 in power 2 gamma over gamma minus 1. Rearranging this expression, we can get another one as this one. M1 over M2 get us 1 minus gamma minus 1 over 2 times M1 times theta. Combining these last two expressions for P2 over P1 and 1 M2, the pressure ratio across the expansion wave at hypersonic speed becomes as that one as the lowest of the bottom of this expression. P2 over P1 get us in parentheses 1 minus gamma without 1 over 2 times M1 and theta, all of these in power to gamma over gamma without E. Yes. Defining as before, M1 times theta as the hypersonic similarity parameter K, hope you remember this, right? We can write next expression for P2 over P1. Get us this, I will remember. 1 minus gamma without 1 over 2 times K in power 2 gamma over gamma minus 1. This equation is for expansion wave, for the shock wave. In both cases, the pressure ratio P2 over P1 is a function over K and gamma. Okay? Yes, we have only two parameters, as you can see. However, whereas our equation for the shock wave assume both high Mach number and small angle, this our expression for the expansion wave assumes only high Mach number, and this equation is not restricted to small angle. And finally, the pressure coefficient Cp from our previous equation get us this large expression. Cp proportion 2 over gamma M1 squared times in parentheses P2 over P1 minus 1. Or we may rewrite it in a next expression. Left part, first component, 2 over gamma M1 squared, the same, identical, right? And this part be transformed in next one. First component, 1 minus gamma minus 1 over 2K in power 2 gamma over gamma without 1 minus multiplying and dividing the right-hand side by theta squared, we can obtain this nice expression for Cp. 2 theta squared over gamma K squared. And second parameters in this bracket, 1 minus gamma minus 1 over 2 times K in power 2 gamma over gamma without 1 minus this very nice expression for the hypersonic expansion wave is analogous to the previous slide for the hypersonic shock wave. Indeed, our equation, this equation, gives a result now becoming familiar that Cp over theta squared is a function from K and gamma for the hypersonic expansion wave. Okay? So, let's come to our summary and some comments. The conventional shock wave and expansion wave relation from basic compressible flow take on simplified but approximate form of hypersonic Mach number. The more important of this form will be listed in a moment. So let's start with the shock wave. In the limit, as you remember before, m1 becomes to infinity. We may write this series of expressions from P1 over P2, P2 over P1, sorry, rho1 over rho2 over rho1 for U2 over V1 and V2 over V2. And this certainly expression for CP. In the combined limit, the same case when m becomes infinity, we may come this in this part. I'm repeating it. So and small angles, we may rewrite this as a beta over theta, get us gamma plus 1 over 2. And defining the hypersonic similarity parameter, yes, this one, m1 theta is identical as k. And we have, in the intermediate case of high but finite Mach number and small angles, as you can see here, next expression for P1, P2 over P1. And the expression for CP, we should note it here that CP over theta square is a function from the K and tau. Okay, I agree? Now, expansion waves. In the case of a high but finite Mach number, we have this expression for theta, 2 over gamma minus 1, in second component, 1 over m1 minus 1 over m2. Here the theta is the deflection angle, and m1 and m2, the Mach numbers upstream m1 and downstream for m2 of the expansion wave. Also, for the same assumption, P1 over P2 over P1 get us expression 1 minus gamma minus 1 over 2 times k. All of these in parentheses get us x power 2 gamma over gamma minus. So here k is exactly m1 times theta. It gets us next expression on the right for CP. 2 gamma, 2 theta square over gamma k square. And second parameters on bracket, 1 minus gamma without 1 over 2 times k in power to gamma minus gamma minus 1 without 1. As the same, you should remember that CP over theta square is a function from two components, k and gamma. Okay? Now, let's come to the next part of our lecture, local surface inclination. You know, a striking difference between linear and non-linear waves concerns the phenomenon of interaction. The principle of superposition holds for linear waves, but not for non-linear waves. As a consequence, for example, access pressure of interfering sound waves are merely additive. In contrast to this part, interaction and reflection of non-linear waves may be lead to enormous increase in pressure. This is not my word. This was a phrase I found in book of Richard Courant and Frederick, even previous century, 1948. And now let's make a model proof. The calculation of the surface pressure distribution over hypersonic bodies, that is the exclusive name of the game from this model. Resulting aerodynamic lift and wave drag are also treated here. And this is our first opportunity in this lecture to calculate such pressure distribution and aerodynamic force. And we do it in the quickest and easiest way possible by cutting directly to the body surface, calculating the pressure there, but nowhere else in the flow field. Okay? All we need to know to calculate the pressure at a point on the surface of a body in each hypersonic free stream is the local inclination angle the surface made at that point with the free stream direction. Sounds very straightforward. Does it now? Okay. But there is no free lunch here. Okay. We pay for this simplicity by sacrificing accuracy. How much? We will see. We will also see that the several methods discussed here are incredibly simple and straightforward. And these simple methods are grouped under the heading of local surface inclination methods. For obvious reasons, in the early days of hypersonic aerodynamics, it was in the 1950s, these methods were about the only thing going. This is how aeronautical engineers in those days made estimates of the surface pressure for the design of hypersonic vehicles. Today, in the world of modern computational fluid dynamics and very sophisticated calculations of complete flow field around hypersonic bodies, the material in this model takes on the role of back of the envelope calculation. This is the modern value of the methods discussed here. For you to carry them around in the pocket of your mind so that you can whip them out at any time to make a quick estimate of hypersonic pressure distribution, lift and weight track. These methods can be used as reality checks in the world of the hypersonic vehicle design and performance. And this lecture is a great way to get off the ground in learning hypersonic aerodynamics. It is straightforward and to the point. It gives you some immediate tools to work with and allows you to make some fun calculations. So, listen and have a fun play. Let's start with introduction. Hypersonic flow is inherently non-linear. This is intuitively obvious when we think of the important physical aspects of hypersonic discussed in first lecture. Aspects such as high temperature, chemically reacting flow, viscous interaction, entropy layers, etc. It is hard to imagine that such complex phenomena could be described by simple linear relations. Even without this consideration, the basic theory of inviscid compressible flow, when the Mach number becomes flat, does not yield aerodynamic theories that are mathematically linear. And this is in stark contrast to supersonic flow, which, for thin bodies at small angles of attack, can be described by linear partial differential equations, leading to the familiar supersonic expression for pressure coefficient on surface or streamline with local deflection angle theta. Get us expression here on the left. Cp proportional to theta over square root from m squared minus. here m squared in V is a free stream Mach number. Okay? And this whole expression is a classical result from inviscid linearized two-dimensional supersonic flow theory. It is simple to easy to apply. Unfortunately, it is not valid at hypersonic speed for reasons to be discussed a bit later. A virtue of this equation is that for a specified free stream Mach number, it gives the pressure coefficient on the surface of a body strictly in terms of the local deflection angle of the surface, angle theta. So that is, within the framework of supersonic deflection angle and linearized theory, Cp at any point on the body does not depend on the detail of the flow field away from that point. And thus, it does not require a detailed solution of the complete flow field. In essence, this equation provides a local surface inclination method for the prediction of pressure distribution over two-dimensional supersonic bodies, but restricted on these bodies at small angle vector. Such simplicity is always welcomed by practicing aerodynamicists who have to design flight vehicles. And this leads to the question. Also, hypersonic aerodynamics is nonlinear, and hence, this our equation does not hold. Are there others, albeit approximate, that allow the rapid estimate of pressure distributions over hypersonic bodies, just in terms of the local surface inclination angle? Right? In other words, is there a valid local surface inclination method for hypersonic application? How do you see? The answer is yes. Indeed, there are several such methods that apply to hypersonic bodies. And the purpose of our lecture is to present these methods. And finally, examine the roadmap gives on this figure. But note that the material discussed in our lecture today, as well as the present module, is itemized for the far left side of the roadmap. Keep in mind that we are still discussing inviscid hypersonic flow, where essentially we are examining the purely fluid dynamic effect of large Mach numbers. Also, a more detailed roadmap for the present lecture is given in this slide. We begin with Newtonian flow, a classic fluid dynamics theory postulated by Isaac Newton in 1687, which resulted in very poor accuracy of low-speed fluid dynamic application over the subsequent century. Only with the advent of modern hypersonic aerodynamic application has Newtonian theory really come into its own. Newtonian theory provides the most straightforward and simplest prediction of surface pressure on a hypersonic. That is why we start with it here. Moreover, we will explore several aspects of Newtonian flow as itemized in the subheading in this roadmap. Two other primary methods for the direct calculation of surface pressure on a hypersonic body are also listed in this slide, namely the tangent wedge or tangent cone and shock expansion method. These methods are slightly more elaborate than Newtonian, but provide inherently better accuracy. The roadmap for this module, in this slide, is relatively short and straightforward, but it is worthwhile to keep it in mind as you progress through the module. Let's start with Newtonian. 3 centuries ago, Isaac Newton established a fluid dynamics theory that later was used to derive a law for the force on the inclined plane in a moving fluid. This law indicated that the force varies as the square of the sine of the deflection angle, the famous Newtonian sine squared law. Experimental investigations carried out by D'Alembert more than a half century later indicated that Newton's sine squared law was not very accurate, and indeed, the preponderance of fluid dynamic experience up to the present day confirms these findings. The exception to this is the modern world of hypersonic aerodynamics. Ironically, Newtonian theory developed 300 years ago for the application of low-speed fluid dynamics has direct application to the prediction of pressure distribution on hypersonic bodies. What is the application and why? The answer are the subject of this model. In proposition for his principle, first published in 1687, Newton modeled a fluid flow as a stream of particles in rectilinear motion, much like a stream of pellets from a stored corn block, which when striking a surface would lose all of their momentum normal to the surface, but would move tangentially to the surface without loss of tangential momentum. And this picture is illustrated in this slide, which shows a stream with velocity v1 impacting on a surface area A, inclined to the angle theta, right? Or the free stream. And from this figure, we see that from Newton's second law, the time rate of change of momentum is equal to the force F, exerted on the surface. So rho times v squared times area sine squared theta. Or we may rewrite this expression in this form. F over area proportions rho times v squared sine squared theta. The force in this second equation requires some interpretation. Newton assumed the stream of particles to be rectilinear. That is, he assumed that the individual particles do not interact with each other and have no random motion. Because of this lack of random motion, this F in this namely equation is a force associated only with the direct linear motion of the particle. On the other hand, modern science recognizes that the static pressure of a gas or liquid is the result of the purely random motion of the particle, right? Motion not included in Newtonian theory. And hence, in this expression for A or F over A, which has the dimensions of a pressure, must be interpreted as the pressure difference above the free stream static pressure. Namely, F over A get us P minus P inverse. P here is the surface pressure. And second component is the free stream static pressure. And hence, we may rewrite this expression into it. P minus P inversing proportions rho inverse times V inverse square times sine square over theta. Or it gets us this expression on the right. Or finally, we may rewrite as this one. Cp proportional for 2 sine squared from theta. And this last equation for Cp in frame here is the famous Newtonian sine squared law for pressure coefficient. What does the Newtonian pressure coefficient have to do with hypersonic flow? To answer this question, recall this figure on the beginning on the slide, which illustrates the shock wave and seeing shock layer on a 15-degree wedge at Mach 33. An elaboration of this picture, which shows the streamlined pattern for the same Mach number 33, flow over the same edge, wedge, right? 15 degrees. And here we see upstream of the shock wave, and this straight parallel streamline in the horizontal stream direction. Downstream of the shock wave, the streamlines are also straight, but parallel to the wedge surface inclined at the 15-degree angle. Now imagine that you examine this figure from a distance, say from across the room. Because the shock wave lies so close to the surface at hypersonic speed, this figure looks as if the incoming flow is directly impinging on the wedge surface, and then is running parallel to the surface downstream, precisely the picture Newton drew in 1687. Therefore, the geometric picture of hypersonic flow field has some characteristics that closely approximate Newtonian flow. Newton's model had to wait for more than 2.5 centuries before it came into our. By this reasoning, this equation on the top, Cp proportional to 2 sine squared theta, should approximate the surface pressure coefficient in hypersonic flow. And indeed, it has been used extensively for this purpose since the early 1950s. In applying previous equation to hypersonic bodies, U is taken as the local deflection angle. That is the angle between the tangent to the surface and the free stream. And clearly, Newtonian theory is a local surface inclination method where Cp depends on the local surface deflection angle. It does not depend on any aspect of the surrounding flow field. To be specific, consider on the left figure A, which shows an arbitrary shape two-dimensional body. Assume that we wish to estimate the pressure at point P, yes, here, on the body surface. Draw a line tangent to the body at that point P, and hence from Newtonian theory, the value of Cp in this point given by 2 sine squared from theta. Now, consider a 3-dimensional body such as sketched on the right part, figure B. We wish to estimate the pressure at an arbitrary point P on this body. Draw a unit normal vector M, vertically perpendicular, to the surface of the point P, and consider the free stream velocity as a vector of V infinity, then we, by definition of the vector dot product, and using a trigonometric identity, we can obtain our first expression here on the top. V infinite times m get us module from V in VC, cosine C psi angle from normal, and get us V upstream sine half phi minus psi, where psi is the angle between normal vector and vector of free stream. The vector n and v define a plane, and in that plane, the plane angle theta will be half phi minus psi. This is the angle between a tangent to the surface and the free stream deflection. And thus, from our equation here, we get expression on this mark. Or simplified in more compact sign it here. Sine theta proportional V free stream over module from this stream times the normal vector. So the Newtonian pressure coefficient at point P on the three-dimensional body is then Cp 2 sine squared from theta, where theta is given by this equation. Okay? So, in the Newtonian model of fluid flow, the particles in the free stream impact only on the frontal area of the body. They cannot curve around the body and impact on the back surface. And hence, for that portion of a body that is in the shadow on the incident floor, as you can see here as a shadow, right? Such as the shaded region sketched in this picture. No impact pressure is felt, and hence, over this shadow region, it is consistent to assume that pressure here will be as a pressure inverse. So, therefore, the Cp equals 0. Okay? So, here will be 0. It is instructively to examine Newtonian theory applied to a flat plane, as sketched in this slide. Here, a two-dimensional flat plane with chord length c, you see it, yes, chord length c, as it at angle of attack alpha to the free stream. Because we are not including friction, and because surface pressure always acts normal to the surface, the resultant aerodynamic force is perpendicular to the plane. And that is, in case the normal force M, yes, the resultant aerodynamic force. For an infinitely thin flat plate, this is a great result that is not limited to Newtonian theory, or even to hypersonic flow. In turn, the vector F is resolved into the lift and drop, vertical lift and drop, denoting here by D and L, respectively. As shown in this figure, and according to the Newtonian theory, the pressure coefficient on the lower surface, it will be CPL of the lower surface, get us 2 sine squared from alpha. And that on upper surface, which in the shadow region, yes, in upper surface here, Cp from upper must be equal to 0. Defining the normal force coefficient as Cm, get us M normal force over Q times S, as here is C from unit, 1 unit. We can readily calculate here by integrating the pressure coefficient over the lower and upper surface. For example, let's see as derivation as here. Tn, 1c integral from 0 to c, cpt minus cp upper for d. X here is the distance along the chord from the leading edge. And substituting this equation in last one, we get expression for Cn 1 over c in parentheses 2 sine square alpha times, or Cn will be equal to sine square from the alpha. From the geometry, we see, sorry, yeah. So we see that the lift and drag coefficient defines as CL is equal L over Q times S, and CD, coefficient of drag, D drag over Q times S, respectively. Here we may found that the S is a C from one unit, and we can get this expression CL proportional Cn cosine alpha, and for CD, Cn cosine alpha. Substituting the last equation and this last one, we get expression for CL in next form, CL proportional to sine square alpha times cosine alpha. And for CD, we can get 2 sine in cubic power alpha. And finally, from the geometry of previous slide, I get it with this, the lift to drag ratio will be given by LD, lift to drag ratio, as a cotangent of alpha. Right? But you should know, in this equation, the general result for inviscid flow over a flat plate. For such flows, the resultant aerodynamic force is the normal force N. Right? You can see here. From the geometry shown on this picture, the resultant aerodynamic force makes the angle alpha, you can see it's opposite here, with respect to lift, and clearly from the right triangle between lift, drag, and normal force. And we have this expression, lift to drag, as a cotangent from alpha. And hence is not limited in our Newtonian theory, okay? The result just obtained above there for the application of Newtonian theory to an infinitely thin flat plate uploaded on this slide. You can see for infinite plate. And from this figure, note the following aspect. The value of L to D lift drag factor increases monotonically as alpha decreases. And indeed, L to alpha became to infinite as alpha became 0. However, this is misleading. When skin friction is added to this picture, drag becomes finite at alpha equals 0. And then L to D factor must be equal 0 as alpha comes to 0. The lift curve peaks about 55 degrees, right? To be exact, it can be shown from Newtonian theory that maximum CL occurs when alpha equals 54.7 degrees. The proof of this is left as a homework problem, okay? It is interesting to know that alpha approximately 55 degrees for maximum lift is fairly realistic. The maximum lift coefficient for many practical hypersonic vehicles occurs at angles of attack in these neighborhoods. And next one examines the lift curve at low angle of attack. So CL, low angle attack, it says the range from alpha from 0 to 15 degrees. We know that the variation of CL with A is very nonlinear. Exactly, right? And this is in direct contrast to the familiar result for subsonic and supersonic flow, where for thin bodies at small alpha, the lift curve is a linear function of alpha. Recall, for example, that the theoretical lift slope from incompressible thin airfoil theory is 2 pi per radian. And hence, the nonlinear lift curve shown in this slide is a graphic demonstration of the nonlinear nature of hypersonic flow. Consider two other basic aerodynamic bodies: the circular cylinder of the infinite span and the sphere. Newtonian theory can be applied to estimate the hypersonic drag coefficient for this shape. The results are as follows. Circular cylinder of infinite span, we have CD from drag over QS, or S proportional to R. Here R is the radius of a cylinder. And CD in this case, from the Newtonian theory, get us 4/3. For sphere, CD proportional to D over QS, S is a pi R squared. R here is the radius of square. And from the Newtonian theory, CD here equals 1. The derivations of these drag coefficient values are left for homework form. Try to do it for your interesting expression. The preceding results from Newtonian theory do not explicitly depend on Mach number. Of course, they implicitly assume that Mach number is high enough for hypersonic flow to prevail. Outside of that, the precise value of M Mach number does not enter the calculation. This is compatible with the Mach number independence principle to be discussed in next lecture. In short, this principle states that certain aerodynamic quantities became relatively independent of Mach number if M invisible. That's it. If the mate sufficiently large, Newtonian's results are the epitome of this principle. Now, let's start with modified Newtonian. Lester Lees proposed a modification of Newtonian theory, writing this nice expression: Cp proportional Cp maximum times sine square from Cp. Here, Cp maximum is the maximum value of the pressure coefficient, evaluated to a stagnation point behind a normal shock wave, and that is expression as this one. Here, the PO2 component is the total pressure behind a normal shock wave at the free stream Mach number. From the exact normal shock wave theory, the related height 2 formula gives this large expression. Two main components, this power gamma over gamma minus 1, and this next one. Notice that we know, noting that the half rho v squared get us half gamma pm squared, and we can become Cp maximum as this expression 2 over gamma m squared, and second component PO2 or P inverse minus 1. Combining these last two equations, we obtain expression for CP max in large formula. And this relation plotted on this right figure here. But we should note that in the limit as m becomes to the infinite, we have CP max in this expression, gamma plus 1 squared over 4 gamma in power gamma times gamma without a 1 times second component 4 over gamma plus 1. And for gamma 1 and 4, get us value CP max 1.839. For gamma equal 1, we get CP max equal to this equation with CP max given in our expression is called the modified Newton's law. And from here we should note the following. First, the modified Newtonian law is no longer Mach number independent. The effect of a finite Mach number enters through our equation as before. This logic deviation for previous slide. Here, CP maximum in this expression. Okay. And second, as both Mach number became to the infinite and gamma became to 1, our equation get us expression for CP get us 2 sine squared theta. And that is the straight Newtonian law is recovered in the limit in case Mach number became to infinite and in case gamma became to 1. For the prediction of pressure distribution over the blunt nose body, modified Newtonian, our equation is considerably more accurate than the straight Newtonian equation. And this is illustrated in this right figure, which shows the pressure distribution over the paraboloid at Mach A. The solid line is an exact finite difference solution of the blunt body, fluid, and the solid symbols are the modified Newtonian result. But we should note it here, the excellent agreement, particularly over the forward portion of the nose. The dashes line is a straight Newtonian result. It lies nearly 9% above the exact result, as you can see. And clearly, from the proper physics of the flow, the pressure at the straight stagnation point of the body is equal to the stagnation pressure behind a normal shock wave. And that is the PO2 given by equation in previous slide. Okay? And this yields the exact pressure coefficient at the stagnation point. And therefore, it is rational to simply replace the coefficient 2 of our expression here with the value for CP maximum, as shown in this expression for CP maximum. And this forces Newtonian theory to be exact as stagnation point, as can seen in this figure. The variation of CP away from the stagnation point closely follows a sine squared decay. Now let's come to another topic of today's lecture, centrifugal force correction to Newtonian. In the derivation of the straight Newtonian law, we considered flow over a flat surface, such as the model sketch of this figure A on the left part of this slide. However, we proceeded to apply our equation here to carve surface, such in the next figure on the B. However, we proceeded to apply our equation to carve surface. And how do you think? Is this theoretically consistent? How do you think? I think the answer is no. For flow over a carved surface, there is a centrifugal force acting on the fluid element, which will affect the pressure on the surface. For an application of Newtonian theory to carved surface, that is totally consistent with theoretical mechanics. And we must modify the discussion to take into account the centrifugal force effect. And this is the purpose of the present section of lecture. Moreover, the results of this section are needed to support the discussion in the next section, or next module on the real meaning of Newtonian theory. To physically understand the nature of centrifugal force on a flow field, consider a fluid element moving at velocity v. Yeah, how do you see movement? Yes, we have this velocity v along the curve as a streamline with radius curve r h in this field. The fluid element is experiencing a radial acceleration. Radial acceleration will be v squared over r radial squared, right? With an attendant centrifugal force in the radial direction. To balance this centrifugal force and keep the fluid element moving along the streamline, the pressure P plus delta P on the top surface of element must be larger than the pressure P on the bottom surface, right? And that is, there must be a positive pressure gradient in radial direction. One could then theorize that in the flow over convex surface, the pressure would decrease in a normal direction toward the surface. And this is a general fluid dynamic trend, not just limited to Newtonian theory. However, it is especially true for the mechanics associated with the Newtonian model. For flow over a convex surface, we should expect the Newtonian pressure to be decreased as a result of the centrifugal effect. And this is derived as follows. Consider in this figure, which illustrates the Newtonian flow over a curved surface. Consistent with the Newtonian model, all particles that impact the surface subsequently move tangentially over the surface in an infinitely thin wire. For the time being, assume this wire to have small thickness df. Later, we will let the df, d delta m become to 0, consistent with the Newtonian approximation. Okay? Therefore, in our figure, we are considering a thin layer of flow over the body, bounded by the dashed line and the body itself. For clarity of presentation, the thickness of this layer is greatly magnified. Okay? Consider point I, this is the body. So at point I, we wish to calculate the pressure Pi. Through point I, consider a streamline coordinate system where S and M, F and N, we have F, and N we have here. Yeah, streamline coordinate drawn from the point I over the distance delta F. As a result of this assumption, because the surface at point I is at the angle theta I with respect to the free stream, then the angle at point 2 may be outer edge of the layer. But here we have the dashed line. With respect to the free stream is also theta I. The same theta I and here theta I. Now, consider a streamline within the layer, as shown in the shade region. In the free stream ahead of the layer, the height of this stream Q is delta dy, delta phi, where y is the coordinate perpendicular to the free stream. Yeah? And the velocity of V infinity. Immediately upon entering the layer, the slope direction is assumed to be theta. And the local deflection angle of the body at that location and the magnitude of the velocity is V infinity times cosine theta, right? And it will be consistent with the Newtonian model, where the stream tube crosses the normal coordinate and drawn through point I. The thickness of the stream tube is dm. And the velocity is v. Concentrate on this part of the stream tube. That is where the crosses M. At this location, Newton's second law, written in streamline coordinate for the motion of a fluid element, is the normal direction, dp over df, proportions rho v squared over r. And this equation states that the centrifugal force per unit volume of a fluid element, rho v squared over r, is exactly balanced by the normal pressure gradient, dp over df. Integrating this equation across the layer point I to point 2, we get this expression. Integrate from pi over p2, dp get us integral from 0 to delta m, rho v squared over r dm. Assuming two-dimensional flow, the constant mass flow through the shaded streamline dictates that the rho v dy get us pv dm. And substituting this equation into previous one, we get us next expression for P2 minus P1, integral from 0 up to y sub I plus delta n cosine theta from rho v over r v dy, where the direction of integration now becomes the vertical coordinate y. But we should note that the vertical coordinates of points I and 2 will be y sub I and y plus delta n cosine theta, respectively, right? Recall that is the incremental height of the stream tube measured in the free stream, and that all of the mass flows through the section of the layer of thickness delta n. Above point I originates in the total vertical extent of the free stream from the bottom line up to point. And hence, in this equation, the limits of integration are taken from y equals 0 to y proportional y sub I plus delta n cosine theta I. making the assumption of an infinitely small thin layer, we let that delta m becomes to 0, or more correctly, y sub I many times higher than delta m times cosine theta. In this limit becomes expression for P2 minus Pi. It will be integral from 0 to y sub I from rho v over r times v dy. And now we make another assumption consistent with the Newtonian motion, because Newtonian theory assumes inelastic collision of the particle with the surface wherein all of the normal momentum is lost, but the tangential momentum is preserved. And it is consistent to assume that the velocity of any given particle after collision is constant. And hence, we can assume that the flow velocity along the shaded streamline inside the layer is constant. And that is, we may write as the v proportional to v inversely times cosine theta along the stream Q, including the section above point R. It is, and recording that R is assumed constant for all streamline crossing and above point I, we become to next expression for P2 minus Pi. So this constant, rho v squared over r, integral from 0 to y sub I, from cosine theta down here. Recall from definition of radius of curvature at point I, we write this expression in this form. R will be minus 1 over d theta over ds in point I, or it equals minus 1 over d theta to dy in point I times sine theta I. And substituting, combining plus derivation and rearranging, we get expression from Pi. Pi will be proportional P2 plus rho v, where times d theta to di in point I, times sine theta I, times cosine from 0 to y sub I from cosine theta dy. Now, subtracting p infinite from both sides of this equation and dividing by q infinite, we obtain the pressure coefficient in this form. Subtracting p infinite from both sides, and dividing, we get this expression. So finally, at point 2, the flow is just entering the layer and is being deflected to the angle theta, namely in point theta I. And there is no centrifugal effect at this point. And hence, from Newtonian theory, the pressure coefficient at point 2 must be interpreted as the straight Newtonian result given in this equation, namely proportional to sine square times theta in point I. With this, our equation rearranged in this form. Our equation, this equation, is the Newtonian pressure coefficient at point I on a curved two-dimensional surface, taking into account the centrifugal force correction. The first term of this right-hand side is the straight Newtonian result. The second term is the theoretically consistent correction for centrifugal effect. An analogous equation for axisymmetric body get us a next expression. Okay? So our here equation can be written in terms of the local cross-sectional area, proportional pi y sub 2, and get us next expression on the bottom of this derivation and previous one. It's one of interesting homework problem. It gets us to remember some experience. Try to. Okay. So the results embodied in our last equations here. We were first obtained by Adolf Busemann in 1933 with analogous approaches given in his two publications. For this reason, Newtonian theory as modified for centrifugal force effect is frequently called Newtonian Busemann theory. We should point it here that from these last equation, that Newtonian theory with the centrifugal modification is not totally a local surface inclination result. The value of Cp in point I depends not only the local inclination angle theta I in this point, right? But also on the shape of the body upstream of point I through the presence of the integral term, as you can see on this part of the end. In some sense, this is compatible with the true physical nature of steady supersonic and hypersonic flow, where conditions at a given point are influenced by pressure waves from the upstream region, but not from the downstream region. Because that information cannot propagate upstream in steady supersonic flow, by the way. However, do not miss this aspect of Newtonian Busemann theory that nothing to do with the true physical picture of the propagation of information via pressure waves. Indeed, such propagation is not a part of Newtonian. Rather, the integral terms in our equations here are simply expressions associated with the mass flow through the layer immediately above point I. And this mass flow depends on the velocity profile along normal vector. In the Newtonian model, recall that we assume that the flow velocity is constant along a streamline inside the layer, and hence the value of V at a given normal depends on the location, and hence the local value of theta, right? Where the streamline first enters the line. And this is how the dependence of Cpi on the shape of the body upstream of point I enters the formulation. So our last two equations, taken on a particular simple form for slender bodies, where theta here is so. For small theta, we may write as sine theta in point I will be simple as a theta at point, and integral from 0 to y sub I from cosine theta to dy get us simply y sub I. And also, letting dc be an incremental length along the surface, we may write as dy proportional sine theta times dc. Yes. And hence, sine from theta in point I times d theta over dy in the same point will be d theta to df in point I, or simply kappa in the curvature of the surface at point I. And thus, our final two expressions become, with dropping the subscript, get us expressions, this one for CP, 2 in parentheses, theta square plus kappa y for slender u. OCP equal 2 theta square plus kappa y for slender bodies of revolution. Right? For flow over a blunt body, the centrifugal correction actually makes things work. For example, left figure shows predictions for the pressure coefficient over a circular cylinder based on all three types of Newtonian light flow: Newtonian, modified Newtonian, and Newtonian-Busemann. These results are compared with an exact numerical calculation carried out by Van Dyck for m equals in this. Note from that Newtonian theory gives the correct qualitative variation, but is off by a constant factor time, and that modified Newtonian is quite accurate. However, the Newtonian-Busemann results are neither qualitatively nor quantitatively correct. A similar trend occurs for slender body cases, as shown in the right side of this slide. Here, the pressure distribution over a 10% thick big convex airfoil is predicted by both Newtonian and Newtonian-Busemann theories and compared with exact numerical results from the Missoudov characteristic. For gamma equal 1.4, the Newtonian-Busemann is again worse than straight Newtonian. And in this right figure, the Missoudov characteristic results are obtained and the Newtonian results demonstrated here. So, on light of the results shown in both figures, we conclude that the centrifugal force correction to Newtonian theory, but also correct from the point of view of theoretical mechanics, is simply not valid for practical application. And for this reason, the centrifugal force corrections are rarely, if ever, seen in contemporary applications of Newtonian theory for hypersonic vehicle design. And therefore, why we have spent an entire section of our lecture discussing such correction. Is it only an academic course at best? How do you think? In my mind, the answer is not. And this is the subject of the next lecture. Okay? I think it's enough for today. And I hope you enjoyed this lecture. And I'm looking forward to seeing you next time. Bye.